Okay, so on 3.2, we're going to continue our talk a little bit about derivatives. And in the last section, we looked at what a derivative was. I'm going to review the derivation of a derivative. We're going to crunch out a few more derivatives, then we're going to talk a lot about graphing derivatives and a little bit more about differentiability. Okay? So, in this class, the definition of a derivative function is limit h goes to 0, f of x plus h minus f of x over h. That's a real big formula in calculus that you need to make sure you know. I won't ever give you this formula because it's such a big deal. And remember, f prime is how we represent a derivative. There's other ways too that we'll learn a little bit later on. So let me just go through the derivation of this. And I want to do this one more time because I like students to make sure they understand the concept behind a derivative. So what I'd like you to do is let's just draw a function and label that f of x to begin with. All right. So the development of the derivative idea goes like this. Let's just pick a dot, and it doesn't matter where the dot is, and just go straight down to the x-axis. And let's label that as x equals let's just use x, okay, on this, since we're defining a derivative on this. So let's just do x there, okay? Then what you want to do is move over to the y-axis, and of course that gives you a y value, but what it is really is it's y equals f of x. It's a function value. So that means what you get then is this point has an x value, just some x value, and it has some y value represented by its function value. So that's how we're going to write that out then. Okay, the idea is h is, some positive number. It's bigger than 0, and we can kind of adjust that h. So what we're doing is we're kind of moving this over. We're adding h to this. So what that does is gives us another dot on the function. Let's just put another dot over here and kind of do the same idea. Just go straight down here to the x-axis, and then that's going to become x plus h. We're adding h to x to move this point over to the right. Okay, then what you want to do is again follow that over to the y-axis like this, and that will give y equals f of x plus h. Okay, you're evaluating that function at x plus h. So that's the setup, and then this point right here could be represented. It has an x value of x plus h. It has a function value of x plus h like that. Okay? So the other thing that you want to consider on here is what we have. We start with what we call a secant line. So you want to just draw a line that kind of goes through like that, and that will be what we call, to start with, that's what we call a secant line. Okay, now let's go ahead and derive this formula then. So actually what we do is we find the slope. We're looking at the slope of the secant line. And of course the slope formula, we're just going to use that slope formula. So it goes like this. These are our 2 points. The y values are those things, so we just subtract the y values. I'm going to do it in this order. Okay, and then the slope formula also says find the change in x. The x values are represented by those things that I highlighted in green. So we subtract it in the same order. We get x plus h minus x, and then that gives the slope. And there's one basic thing that happens on this is the x's cross out. So what we actually get is the slope of this secant line is equal to this expression, f of x plus h minus f of x all over h. Now this is given a function that will give the value of a slope of a secant line if you know those particular points. This is just a general formula for that then. Okay? So what we're going to do on this then is I'm going to open up this applet, and this applet will kind of help us, I think, to understand something. I think this does a pretty good job of doing this. So let me do this. That's not the one I wanted to do. Here's the one I want to do right here. Okay. So this is going to kind of just do what we just did here. So what we do is we have some generic function. We have some point. We're going to call that a this time. And then you have a function value f of a. Okay? H is just some positive value, and we're going to have the ability to kind of adjust that as we go. And then we go the next thing. Whoops, I went too far. Crap. Okay, all right, so that's where I was. Okay, now I'm at H. Now I go to the next thing. A plus H just means the point moves over, and you have a function value. That's what I just did. Now what we do is we get a secant line. Now that's kind of where we were so far. Now the idea on this is H gets smaller, this point moves closer to A. So you're going to see this secant line changing, and as H gets smaller and smaller, this thing gets closer to a tangent line. A tangent line can be thought of as 2 points that are infinitesimally close to each other. This slider doesn't let us go to 0. If you went to 0, you wouldn't have a tangent line, but if you went to 0.00001 and so forth, you make it as small as you possibly can, then for all practical purposes, this becomes a tangent line. And that's what we're looking for, is the slope of the tangent line. That's why we let the limit H go to 0. So hopefully that will help you all out a little bit to see that. H goes to 0 makes this into a slope of a tangent line then. Okay? All right, so what we do then is, to get the slope of a tangent line, then we just take this expression, which is an expression, a function that's given us the slope of a secant line, and we let that limit go to 0. H goes to 0. So that's the definition of a derivative. We looked at that in the last section. It's important enough that I wanted to show that one more time and just give a couple of definitions. Okay, here's some basic thoughts that you want to be in vocabulary. This is called the difference quotient. Generally, students learn about that in a pre-calculus class or a college algebra class. You don't really learn too much where it comes from and what it does, but we like to get people comfortable with that. So this gives a slope of a secant line. That's what I just showed you. And a secant line is just, you got 2 points on the curve. Okay, 2 points on the curve. And that's what I did with that derivation. I just sort of randomly picked 2 points. Okay, and that gives what we call an average rate of change. All right, now when we do the limit, then that's called the derivative. So that's the derivative function. Sometimes you'll hear this called the derived function. So that's the derivative. It gives the slope of a tangent line, and it actually gives an instantaneous rate of change. All right, so there's a difference between average rate of change and instantaneous rate of change. For average rate of change, you're considering how things are changing between 2 points. Instantaneous rate of change, you're looking at the rate at one particular point. So that's the idea. Okay, the last thing is this. For now, we're going to notate that as f prime of x. We'll learn a little bit different type of notational system a little bit later here. Okay, so before I go to the next page, I want to open up, I think, this applet. And this just shows you, basically what the tangent line looks like on a particular function. Okay, and you have the ability to kind of move this value of a over within the graph like that. So right now you have a positive sloping tangent line, and what happens is that tangent line changes throughout the function. Okay, you can see how that tangent line is changing, and that means the instantaneous rate of change is continually changing on that then. And then you can put in this particular applet any kind of function that you want to. So the idea is, I want you to know that what happens is that tangent line its slope continues to change. Okay? All right, now we're going to move to the second page on our notes. And we're just going to do some derivation. Okay, so we're going to go over some basic derivatives. Now, when we get to the next section, I'll be going over derivative rules, and we'll kind of get away from doing this difference quotient. But the difference quotient we're going to use a lot for derivations of derivative formulas. So let's go ahead and get these set up and kind of see how we do with this then. So this first one is a linear function, y equals mx plus b. So again, a good way to start all these problems is just write down the difference quotient. Write down the definition of the derivative. So it's the limit h goes to 0 of f of x plus h minus f of x and all over h. Okay? Now, the key thing on this with the setup, sometimes students, when they're learning this, have some struggles with understanding how to set this up. So I'll show you this way. This is the way I like to get students to think through these problems. When you plug into this derivative formula, it's a good idea to just write that like that. You have, in that numerator, something minus something all over h. Okay, well, the formula says that f of x goes here. Okay, and there's no question on that what f of x is. That's mx plus b, so that just goes there. Okay, then it says f of x plus h goes here. Well, the only difference between f of x and f of x plus h is that x gets changed to x plus h. So this is the same. It's m times something plus b still, but what you change that to is x plus h. Now look at that real carefully. This is the function. This is the function where x became x plus h. That's it. Okay. Now what you do is algebra, and what's going to happen from here, this one's not too bad. If you multiply this out, you would have mx plus mh plus b, and then minus mx minus b, and all over h. Okay? Basic algebra distributive property. You see anything canceling out, you almost always will. So the mx's go to 0, that goes to 0. So it looks like we're left with the limit. H goes to 0, and we're left with mh over h. Okay, the h's divide out. So what you're left with then is the limit of m as h goes to 0. Now, anytime you have the limit of a constant, it's just that constant. So I like to show this example because hopefully it'll make sense to you. The idea is, well, what is the slope of this line? That slope is m. Okay, so I hope that makes sense to you. Okay, the slope of the tangent line will always be the same as the slope of the line on this particular problem. So that's how that works out. That's a good illustration to show students. Okay, so we expect that derivative to be m. Okay, let's run through the next one. The algebra is a little heavier on this one. So again, I would recommend that you go, just write down the definition. Limit, h goes to 0, f of x plus h minus f of x, and all over h. All right, and then we'll just put this together. So again, this is my strategy. The way I like to get students to think through this is just put 2 parentheses here, or 2 brackets is what I usually do. And then you just got to put stuff in the right place. Okay? So remember, f of x goes there. F of x is what I gave you. So that means x to the second goes there. Okay? F of x plus h goes there. So all that means is it's the same thing, except it's x plus h squared. Okay, so those things, that's f of x plus h. Then you got to work this stuff out. Now there's a lot of algebra that goes on these problems, so a couple of things I want to do at the side here. You can do scratch work just kind of at the side of your paper on some of this, so you need to FOIL this out. There's 2 ways to do this. There's a shortcut, and then there's just writing it out twice in FOIL. So this goes like this. First term, x times x to the second, Outside term is plus xh. Inside term is also xh. And then the last term, h times h, is h to the second. So you get x squared plus 2xh plus h squared. You need to be totally on top of factoring and foiling and multiplying out polynomials and stuff in this class. So what we're going to do then is, this is what I just did, this part right here. So let's replace that in our next step. So the next step we would have is the limit as h goes to 0. Change this to x squared plus 2xh plus h to the second. Bring down the minus x to the second. And then this will be the limit that we're ultimately going to do then. Okay? I do want to show you this also. There's a way to do this in your head. And as a calculus student, you want to get to where you can do this. Okay, you square the first term, that's x to the second. You square the last term, that's h to the second. Then you multiply those together, but then you double it. That's the shortcut you can learn on there, so you get it real fast if you apply that shortcut. Okay? All right, now back on our problem, what happens? This cancels, that goes to 0. So we're left with the limit. H goes to 0 of 2xh plus h to the second all over h. All right, now what happens on these problems is somehow we got to get this h to cancel out. Right now, and I hope you can do this in your head, if you just plugged 0 in for h, well, what would happen is you would get a 0 over 0 limit, and we said in general, you know, most of the time your 0 over 0 limits are going to exist. There are times when they don't, but, you know, most of the time when you encounter it, you're going to be able to do some algebra and this limit will exist. So what do? You factor an h out. Okay, so we got to do factoring. And see how I keep just bringing the limit down? Don't be lazy about how you write steps. Write your steps the way I'm trying to show you. So we have h times 2x plus h all over h. H's divide out. That's what we were hoping for. So we end up with the limit of 2x plus h as h goes to 0. And then again, what you do is just replace h with 0. So you get 2x. So the derivative is 2x. So what you find here is f prime of x is equal to x squared. Okay? So that's how it goes, all right? Now we're going to learn a shortcut on this. I mean, it's that I'm going to keep you in suspense though a little bit, okay? Next section I'll show you how to do this problem in like 2 seconds. All right? Okay, so let's move down to the next thing. Always pause the video if you need to slow down or something. That's the benefit of videos and online classes. You can pause the teacher. You can put me on hold anytime you want. Okay, so let's go to this next one here. I'm going to do a couple of more and then let you do a few more of these. And then we'll get to the newer things in this section. But I do want to spend some time on this, though. Okay, so this one we're doing a square root. Let's start again by writing down the definition of a derivative. In your homework, you don't have to do this. It's just, you know, this is kind of a good approach, a good way to present your work. Okay, so what we're going to do is, again, I'm going to show you how to set this up. And you always got to make sure that you set these things up correctly. All right, this again is my recommendation. Just kind of build the framework for how this goes in the formula. Okay, f of x always goes there. F of x I give you. So whatever function I give you goes there. Can't go wrong with that. Okay. Then the other thing that I've been showing you is this is where f of x plus h goes. So what's f of x plus h? It's the same as the square root of x, but you replace the x with x plus h. Okay, so there's your setup, and if we can algebraically work with this limit, then we should get a derivative. Okay, so I think we looked at this a little bit in the last section. This is worth going over again because of the algebra. So we have the limit of x plus h minus square root of x all over h. We have a 0 over 0 limit right now. I mean, if you think about it, if you just replaced h with 0, you'd get 0 over 0. You can do that in your head. Well, turns out what we got to do is, there's a little trick to this. You need to make those radicals go away, so we multiply by what's called the conjugate. The conjugate just means multiply by exactly the same thing with one difference. Instead of that being a minus, do a plus. And then something is going to work out. Something magical is going to happen. Okay. So that's how that thing gets set up, is like this then. Okay. Now, we got to go through the FOIL on this a little bit. Now, I'm going to do this at the side. Again, this is kind of scratch work that you can do at the side. With practice, you can start doing this in your head, and I'm going to show you how to do that. Okay, so I'm just going to kind of write this out the side. You might want to write this down in the problem or somewhere. Whoops. But this is usually an area that students need some review on. So we're multiplying and we're just foiling this expression out. Okay, so let me take you through how the FOIL works on this then. So this is the first term. And what that would be is the square root of x plus h times itself. Well, the radical's going to go away, right? Okay, the outside term is this times this. Now, they're both under a radical, and you don't have to put them together. You can just write this as square root of x plus h times square root of x. That's good enough. Okay, the inside term is the same thing, except it's a negative. So you'd have minus square root of x plus h times square root of x. Those things are going to cancel out. Okay, and then the last term is going to be minus. You have a positive times a negative, so it's a negative square root of x squared. Okay, that's it. Write it out until you get to a point where you can do this in your head. That's going to cancel, and it always will on a conjugate. This is going to be x plus h, and then that's going to be minus x. Okay, that's what's going to happen on that problem then if you FOIL that out. So if you go back to our problem now, of course that's going to cancel that out. So you're going to end up with the limit as h goes to 0 of, and let's see, we have an h left over in the numerator. Then we have the denominator, we have h over square root of x plus h plus square root of x. So that's what we get. Okay, I want to show you a way that you can do this in your head. Okay, now if you ever encounter something like this, if you have a plus b times a minus b, that's the form we just did here. It's just kind of, you do the first is a squared, you do the last is minus b squared, and then the outer and inner cancel out. Okay, so you can do that in your head. That problem right there, getting that value with the FOIL, you can do in your head. Okay, so over here what happens? The h's cross out. Write what you're left with. So we're left with the limit as h goes to 0 of, and we're left with a 1 over square root of x plus h plus the square root of x. Okay, now what do? Now you're ready. Once you kind of get to that point, now you're ready to replace the h with 0. And if you do that, you can do this in your head. It's just square root of x plus square root of x. Those are like terms. You have 2 of those, so you would get as an answer 1 over 2 times the square root of x. And this is another example of a problem we're going to learn a totally different approach to this problem, where you'll generally just be able to do that in maybe 10 seconds and get that answer. We're not there yet. I want to keep you in suspense. Okay? All right, so I'm going to do one more, then I'm going to let you do a few of these yourself, and then we'll go to the next major topic, which is graphing derivatives. That's kind of the new thing that we're going to do in this section. Okay, so let's see what we got here. This is another good algebra exercise for students. So let's write the definition. F prime of x is equal to the limit h approaches 0 of f of x plus h minus f of x all over h. Okay, let's get this put together. Little algebra skill is required on this. Okay, so we have limit h goes to 0. Again, let's do the setup the way I've been showing you how to get this set up. That's step one, is make sure you know how to set these things up. Okay, same thought process. F of x goes here. F of x is what I give you. So that's 1 over x plus a. Okay. F of x plus h goes here. That's the same thing except replace x with x plus h. Okay, so that means this is going to be 1 over x plus h plus a. Okay, so all I did was replace this x with x plus h. That's it. Now, what would happen here is you do have a 0 over 0 limit. That's a worthy thing to just try to do. Just replace those two h's with 0 and see in your mind if you don't see we have a 0 over 0 limit. So we're going to do some algebra on this one, and this has to do with how you deal with what's called a complex fraction. So let's write this as 1 over x plus h plus a minus 1 over x plus a all over h. So the idea on this is we want these things to go away. I'm going to erase all this scratch stuff I did over here. And I'll show you kind of the thought process that I have on this then. So let me get rid of this crap. Not crap, that's good stuff. All right, so here's the idea. If you have 1 over x plus h plus a, like we do, and you want that denominator to go away, well, then you just multiply by it. Okay, I'd get rid of it. And then you have 1 over x plus a. If you want it to go away, you multiply by x plus a. Now, we have to, those are totally different things. X plus h plus a, x plus a, those are totally different things. So the only way that we can get rid of both of these at the same time is to multiply by x plus h plus a to get rid of that thing, and then also multiply by x plus a to get rid of that thing. Now, fundamental stuff here, if you're working with a fraction, you have to do the same thing to the top and bottom. You have to. If you don't, you are changing the problem. Simple concept. If you have 2/3, if you multiply by the same thing, 4/6 is still the same as 2/3. But if you multiply by different numbers in the numerator and denominator, then you've changed the value of the fraction. Okay? All right, so this goes like this. All right, you want to try to manage this in your head. A little hard to show. Usually if I'm in class, I tell students to block this out. Just kind of ignore that thing, and what will happen is this will cancel with that. Okay, and that will leave you with 1 times x plus a. That's what you're left with there. That cancels, you're left with 1 times x plus a. Then you distribute here. So you got a minus. Now what happens? This and this cancel. That cancels, you're left with minus 1 times x plus h plus a. Like that. You don't have to put the 1's in there. I'm just doing that mostly for emphasis. And look at that in your head how that goes. Just take your thumb and block this thing out. And then you're taking this times this. That crosses that out. You're left with 1 times x plus h. Block this out. That'll cancel that out. You're left with minus 1 times x plus h plus a. Do that in your head. Okay? Saves you a lot of work on your paper. So we have the limit h goes to 0. This is going to be x plus a. And then you distribute the -1 through there to get minus x minus h minus a all over h. Okay? And don't forget that you still have this in your denominator. Okay, we had to multiply the top and bottom by the same thing. So it's kind of, you got to watch that and make sure you don't make that mistake. And I should have really written that in the previous step like this. Okay, I should have done that. Okay, so let's write that out. So we're going to have x plus h plus a times x plus a. And now we're ready to finish up this limit. So notice a lot of stuff cancels out. A's go away, x's go away. Write down what you're left with. So we have limit h goes to 0 of negative h all over h times x plus h plus a times x plus a. All right, what happens? H's go away. They always will if you're going to get this limit to work out. Okay, that's kind of the key. So now, write down what you're left with. We're left with the limit as h goes to 0 of negative 1 over x plus h plus a times x plus a. Now just you have an h that's going to go to 0. Okay, so what are you left with? You're left with negative 1 over x plus a times itself. Now, I kind of did that in my head, but the idea is that's pretty easy to see. That thing goes to 0, so you're left with x plus a times x plus a, so just write it out like that. So that would be the answer to that derivative. Okay, good place to pause if you need to stop and think through what I just did. Otherwise, I'm going to have you go to the next page, and I'm going to have you see if you can set up these two right here and do these. X to the third, you can get into some algebra because you're going to have to do x plus h to the third somewhere in the problem. This one's very easy, but sometimes students have a little trouble setting that up. Okay, so I'll go ahead and pause and see what you come up with on these two examples. Okay, so see if you did this okay. The first one's 0, and the second one's 3x to the second. And I won't go through a lot of the details on here. I just want to kind of give you an opportunity, if you didn't get this right, to look over what I did and see if you understand it okay. The key, I think what students have a hard time with on number one sometimes, setting it up. F of x is c. F of x plus h is also c. It can't be anything different, okay? There's not a x to replace with x plus h. So you end up with a limit of 0, which is 0. And what I want you to understand on this too is if you have a function like y equals c, that just means you have a horizontal line. What is the slope of a horizontal line? It's 0, regardless of what that value of y is. And that's what it is, so it's slope 0. Okay, this one, you want to make sure you set it up like this. F of x is x to the third. Then you have x plus h to the third. Third all over h. This is the key right here. Again, I'm not going to go through the details on that. If you didn't get this, you just need to look over what I did. I wrote it out 3 times, which is pretty well what you got to do. Shortcuts for this, there is such a thing. Nobody seems like they ever teach it anymore. Something called the Binomial Theorem that we used to teach in college algebra. The best approach on this probably for now is just write it out. And you're not going to encounter something to the 4th or 5th or 6th power. When you do, there's going to be a much easier way to do it anyway, okay, for doing a derivative. So I just foiled this. I put it together like this, foiled that, and got that. Then I multiplied this out, collected like terms, I got that. All right, and then you can look over the rest of this. There's some factoring. You get 3x squared. Okay, now here's what's going to happen. Okay, I know you're just dying to know. So here's how you can do this problem in like 4 seconds, or maybe less. Okay, the way you're going to learn to do this, when you have x to a power, you bring that down, and you subtract 1 from the exponent, and you get 3x to the second. That's what you're going to learn in the next section. Isn't that cool? 3x to the second. So like if you did this same problem, f of x equals x to the fourth, that wouldn't be too fun to do this way. Well, the derivative is this. You bring down the 4, you subtract 1 from the exponent, so it's 4x to the third. Isn't that cool? All right. Okay, so that's your shortcut on that. Okay, so the next thing in here is going to be the idea of graphing a derivative. So if you're given a function to help you understand derivatives, we like to have students graph derivatives too. It's a good mental exercise. So a couple things I recommend is find x values where the derivative is 0. That would be where you have a horizontal tangent line. Find intervals where the derivative is positive. That would be tangent lines have positive slope. That would be like the tangent lines are going up like this. Derivative is 0 where you have a horizontal tangent line. Find intervals where the derivative's negative. That would be where the tangent lines are negatively sloping. And then another good thing is the slope is 1 whenever that thing slopes at a 45-degree angle. It's -1, the slope is -1, when it slopes downward at a 45-degree angle. Those are kind of the key things I like to get students to think about when you're graphing derivatives. Okay, so let's see. Let's go down here. Next page, this shows the thought process. So this is a function that you're given. This is the derivative. dy over dx is another way of saying f prime of x. This is the graph of the derivative. So here's what I suggest. Right now, the derivative is 0 because you have a horizontal tangent line. So that means the value of the derivative is 0, meaning it's on the x-axis. Okay, over here, the tangent lines are negative values. Well, so that means that the y value of the derivative is below the x-axis. Okay, out here, the tangent lines are sloping positive. So that means out here, all of the values of the derivative will be positive y values. So right now, you have negative slope. Therefore, you have negative derivative values. Out here, you have positive slopes. Therefore, the derivative has a positive slope to it. The other thing that's happening is the slope is getting bigger. It's getting steeper and steeper, so that's why that's going the way it does. Okay? So again, what I always suggest you do, here's a cubic function. Figure out where the derivative is 0. That's always the best starting point. Right there, the derivative is 0. So that means you're on the x-axis, x-intercept, when you graph the derivative. Same thing there. Okay, you have positive slopes here, so that just means make your derivative above the x-axis. Here you have negative derivative, negative tangent lines, make the graph below the x-axis. Okay, you have positive sloping tangent lines here, so make sure that the derivative's above. So at a minimum, you would want to have show where the derivative's 0, show where it's above, below, and above the x-axis. That's what you want to start with. And then the accuracy is, it's hard to get it perfect, but it's a really good thought process. So see, I do the same thing here. These are the 3 places where the derivative is 0. Okay, so see, I just put an x-intercept when I'm graphing my derivative. Okay, the slope is negative here, so that means you're below, the derivative's below. The slope's positive here, that means the graph of the derivative is above, and so forth. Okay, that's just sort of a rough idea of how to think through those problems. And we're going to look at several individual examples to hopefully get a little bit better idea on this now. Okay, so if we move from here, I'm going to start with, given a derivative, we graph the derivative together. Start simple and build ourselves up to a little bit more complex level. Here's the function. This is actually the function y equals -4. Okay, f of x equals -4. We're going to graph the derivative f prime of x. Okay, well, what is the slope always? Yeah, the slope is always 0. Okay, so if you remember, it's a tangent line. So anywhere that you have a tangent line, that tangent line is going to be the same line, so it's going to be 0. So that means the derivative, the values of the derivative are always 0. So what do? You just graph this. The graph of the derivative would go like this. Okay, f prime of x is 0. It's always 0, meaning you're always on the x-axis. So that goes. That's the graph of that derivative. Okay. Now, the next one, what we're going to look at is the slope changes on this. Okay, remember, a tangent line to a line is just the same line. So we're going to look at this area here, first of all, from -6 to -3. All right, let's figure out what the slope is. Okay, the slope is the rise, 1, 2, 3, 4, I think, 1, 2, 3, 4 over 1, 2, 3. So that's a slope of 4/3. Okay, if I'm looking at that right, I think I am. Okay, so what do? We graph 4/3. 4/3 is about 1.3. So that means on your derivative from here to here, you would graph 1.3. Now you would put open circles on this, and we'll learn about this a little bit later. The derivative is not going to exist here because the slope's going to abruptly change to something else. So the value of that derivative is 4/3. Therefore, we use that y value of 4/3 like that. So that's the first thing. Okay, now we're going to look from -3 to 0. -3 to 0 is what we're going to look at here. Well, we're going to do the same thing. We're going to find the slope. Okay, so that slope is 1, 2, 3, 4 down, 1, 2, 3 over, so it's -4/3. So that means the value of that derivative is always -4/3 in this interval. So you'll do the same thing. It's about -1.3. So you'll go down about -1.3 and then just draw a line like that. The derivative has the same value from -3 to -1 because it has a constant slope. Okay. Now we move the next place. Okay, the next place we're going to go is 0 to 2. Count the slope. 1, 2, 3, 4, 5, 6 over 2. So that slope is 6 over 2. So that slope is 3. So that means from 1 to 2, the value of your derivative is 3 constantly. So it goes like that. All right, and we got one more thing to do. So the next thing that we're going to look at is from here to here. Okay, from 2 to 5, figure out the slope. Okay, so that's count, rise over run. 1, 2, 3, 4, 5, 6, 7, 8, 9. Down 9 over 1, 2, 3. So that slope is -3. Okay, like that. So what do? You just graph like this. The value of the derivative is -3, so it goes like that. All right, now those bubbles, we'll talk about that a little bit more. That's just because the derivative changes values very fast. Okay, so that value of that derivative, that ends up being what we call non-differentiable. You have that whenever you have a real sharp point on the graph where the value changes abruptly. Another way to look at this is, how in the world would you draw a tangent line at that point? Would you draw it that way? Would you draw it that way? Well, you couldn't draw it at all. So that's how that would go. All right, so that's another example that's a good way to help you start thinking about derivatives. Okay, next page, these get a little bit more complex. So what I'm going to do on this is I'm always going to say start off by finding where this derivative is 0. The derivative is going to be 0 wherever the tangent line has a 0 slope. That looks like that happens at 2, around 2. So I'll put a dot there. The derivative is 0, so I'm on the x-axis. And that looks like about a half the derivative is 0. That's how you want to start the problem. Just figure out where the derivative is 0. That's always a good way to figure that out. Okay? Now, figure out where the derivative is negative and positive. So what happens on this is the tangent line is sloping downward here until you get to that place there. All right, so what you have here is you have a negative slope. The tangent line is sloping downward. Now the value of that's changing, kind of like this as we go through this. Another good thing that I like students to kind of look at is see if you can figure out where it's kind of at a 45-degree angle. It's actually really kind of hard to tell that, but it kind of looks to me like that's at a 45-degree angle. At -1/2, it looks like the slope is -1. Okay, and then all these values here are negative. So that means the derivative, and you just estimate this, is going to have to do something like this. The value of the derivative is negative. Okay, and right around here, it's at a 45-degree angle for the tangent line, so I go like that. Okay. The next thing I see is from here to here, then you have a positive slope. So that means the graph of the derivative is going to be above the x-axis. And then it's going to go to 0 again like that. So you just kind of make sure that that part of the derivative is above the x-axis. Okay, and then from here on out, what happens is the derivative is negative. And it gets smaller. Anytime the slope of the tangent line goes like this, the values are actually getting smaller. See, at 2.5, probably at 2.5, we're probably around a 45-degree angle, so that value of that derivative would be negative. So that graph of the derivative would look something like that. That's how you reason that out. Okay. All right, next one. Okay, again, start off by figuring out where the derivative is 0. So what I see is probably there's 3 places where that tangent line looks horizontal. So when x is 0, the derivative is 0. So that means when you graph the derivative, you have an x-intercept at 0. It also looks like at 3, you have an x-intercept. All right? So I'm going to put a dot like there. Same thing here, negative 3. Looks like we have that. Okay? Then just think of this. Okay, what's happening here is the derivative is positive. So that means that derivative has to be above the x-axis in here. Another thing that's kind of good to look at, just kind of estimate where do you think that tangent line's at a 45-degree angle. To me, it looks like at negative 1.5, the derivative is 1. That's what I see. Okay, and what's happening then on this is this derivative is going to go something like this. It's going to go through those points kind of like that. Okay, then the derivative becomes negative. So down here, you're going to be below the x-axis. The other thing I look at is somewhere maybe at 1.5, that tangent line's at a 45-degree angle. That would mean you have a slope of negative 1, and this is estimating too. There's no way to make this perfect. So that graph of that derivative would look like that. That's how you reason that out then. Okay, and then generally, I also want to mention this too. Generally, if you have a end point, this is kind of a picky detail, but at an end point there, we're just going to say, we'll just use open bubbles for the derivative on that. All right, so that's the idea. Okay, this takes a little bit of practice. Now, there's a great website, and I'll post this for you guys, or you can just copy it on here, and this is a really good thing to spend a little bit of time with. So in this particular applet, which I think is a Geogebra applet, you're given a function. And you can move these dots to graph the derivative. So let me show you kind of how I would do this. First of all, I would find where the derivative is 0. Right here, the derivative is 0. Now, you can't move the dots over that way, unfortunately. Okay, but you're going to have a positive slope from here to here. So this is kind of the way I look at it. Is that a 45-degree angle? Probably not. So that derivative right there might be somewhere there. Okay, then somewhere there. Once you get past this point where the tangent line's horizontal, then you're going to have negative derivatives until you get here. So everything in here has got to be below the x-axis. Is there a place from here to here where the tangent line is at a 45-degree angle? Kind of hard to tell. So it kind of looks to me like you might have something kind of like this, possibly. And then you're going to be going back to 0 like this. So once you're here, that derivative is going to have a value of 0. And then from here to there, all of these dots are going to be above the x-axis. They all have to be there. Okay? And I kind of look at this like this. Probably in here, the derivative is close to 1 because it looks like it's close to a 45-degree angle. And it's kind of going this way. And then once you get here, the derivative is 0 again. And then these last two dots are going to be kind of like this. Now, this is telling you the accuracy as I go. So right now I'm 83% accurate. And I didn't even bother, at this point I didn't bother with it. That's pretty close to the derivative being 0. Okay, now I'm 90% accurate. Now what it'll do is it'll show the derivative, and I mean, you never can get this perfect, but if you play with this, you want to try to get this maybe 75% accurate, that kind of thing like that. Okay, so that's a really cool applet to give you a little bit of practice. Okay. Okay, so what I'm going to have you do next here is go on and try these problems yourself. There's 4 problems, I think. Here's the function, graph the derivative. Here's the function, do the derivative below, and then this one. Okay, so go ahead and see how you do on that, and come back and check your answer. Okay, so let's go ahead and see what you did on this. Now, the first couple of problems you can get exact. Like the last 2 problems are more estimation. Okay, getting kind of a rough idea of how that goes. So this is the graph on this, and you got to have this pretty much exactly this way. You probably really should put bubbles at the endpoints. You can't. This is not showing that that's going on forever. So basically, in here you have a slope of 0. So that means graph y equals 0. Okay. Here you have a slope of -1. That means graph y equals -1 in that interval. Here you have a slope of 1. Okay, that means you graph y equals 1 on that interval. And then here you're at 0. Okay, so what you have is basically 0 slope, -1 slope, 1 slope, 0 slope. Remember, I'm graphing the values of the derivative. Okay, the value of the derivative is constant in these 4 regions. Okay, that's what you should have. Okay, the next one. You can also get this one exactly. All right, so my graph is down below on this. So in this region, you're down 3/6, so the slope's -1/2. So that slope is always -1/2 there on tangent lines, so I graph y equals -1/2. In this region, from -2 to 0, the rise over the run is 8/2, so it's 4. So the derivative has a value of 4 in there. So you graph y equals 4. From 0 to 2, it looks like you're going down 10, right 2. So the value of that derivative is -5, so I graph that. And then here, the derivative is 0, so I graph y equals 0. Now that's how that graph has to go. It has to go exactly that way. Okay, number 3 has to have the shape. Doesn't have to be perfect, just has to have the shape. So the way I look at this is there's 3 places where the tangent line would have a 0 slope. Remember, you're thinking about the slope of a tangent line. So at -1, it looks like about -1.5, you need to put, the derivative is 0, so you put a dot on the x-axis. At m equals 0, derivative 0. At m equals about 1.5, derivative is 0. So those things have to be there. And then it's just you have a positive slope in here. So if you have a positive slope in there, that means the derivative has to have positive values, so it just needs to be above the x-axis. Okay, coming down like that. And then the derivative starts having a negative value. So from there to there, you just got to have the graph below the x-axis, just at a ballpark. I also kind of thought maybe in here somewhere the value of the derivative is -1, maybe because it's a 45-degree tangent line. Okay, then what happens is in this region, you're back to positive derivatives, so you need to have that piece of the graph above the x-axis. And then finally, the rest of the way, the tangent lines are negative, so you need to make sure that you're below. So the key thing is kind of know where the graph of the derivative is above the x-axis and where it's below the x-axis. That's the key. And know where your derivatives are 0. So that's basically what you would get on that. It doesn't have to be exactly like that, but just the idea of that shape. Okay, the next one's kind of the same way. So the way I looked at this is there are 2 places on this graph where the tangent lines would be horizontal. Right here, it looks like you'd have a horizontal tangent line. Right here, you'd have a horizontal tangent line. So if x is 3, the derivative is 0. If x is 0, the derivative is 0. Okay? Then again, I kind of do the same thought process. This region right here that I'm highlighting in yellow has a negative derivative, so that means your graph has to be below the x-axis. Then what happens is, well, it's still negative. You still have a negative derivative there. And what's happening is it's just going back below the x-axis again. And it has to be moving downward because that value of that derivative is changing. That derivative is getting steeper, and then it starts getting less steep. Okay, then what happens here is from here on out, the derivative is positive. So from there on out, you've got to be above the x-axis, and the tangent line's getting steeper. That's why the derivative values are going up. They're getting bigger y values. Okay, so that's how that would work out then. That's the graph of the derivative idea. Okay. Okay, so that'll kind of wrap that up then. So on the next page, I'm going to let you do one more thing and see if you can do this activity. What you want to do is you want to match the function. These are the functions right here. So this is f of x, and then these are the derivatives. So you just want to write, which one you think this is. Okay, so I'll give you a little time to do that. Another good exercise for students. Okay, so just check your answers and see if you came up with this okay. That's another good exercise to have students go through and look at. Okay, so I'm going to move on to the last part of this, which is differentiability. Pause and think about that a little bit. I mean, every choice had only one possible derivative on there, so it's just kind of a matching exercise. Last thing is a couple of quick notes about differentiability, which we talked about in the previous section. A function is non-differentiable generally in these situations. If you have a sharp point, we also call that a cusp. Sometimes you'll hear that called a corner. I usually call that a cusp. If you have a place where you're discontinuous, and the other place would be if you have a vertical tangent line. So remember, a derivative is a slope of a tangent line. If you have a sharp point, also hear me call that sharp point sometimes, then it's not possible to draw a tangent line on that. The tangent line, you can't decide how you would draw it. Okay, one way that I like to look at this is we're interested in the differentiability of that point there. Well, you can think of a tangent line as being 2 points infinitesimally close to each other. Well, if you put those things together, the tangent line would have a negative value. If you did a point just barely to the left of that, then you got a positive tangent line. So you really can't make a decision about that tangent line on that. And it's the same thing with this. You can't draw a tangent line to where there's a break in the graph, because if you put a dot there, then the tangent line looks like that. If you put a dot there, then it's a different tangent line. Okay, so it's the same idea. And then this one would be, we know the slope of a vertical line is undefined. Okay, so you can end up with a derivative that's undefined, where that slope is undefined at some particular point. So that's what you look at. Okay, so I'm going to have you do this little exercise real quick. On this, I gave you a graph. Just tell me where it's, the x values where it's discontinuous, the x values where it's not differentiable, and the intervals where it's continuous. Okay, so go ahead and check your answers on this. There's only 2 places where it's discontinuous. There's only 2 breaks in the graph. You have a vertical asymptote and you have a hole. Everywhere else, it's smooth and connected. All right, non-differentiable is different. You're non-differentiable wherever there's a break. There's a break at -2, and there's a break at 2. So these 2 things here, those are places where there's a break in the graph. Okay. The other things you look for are sharp points. At -1, you have a sharp point. The other thing you look for is where you have a vertical tangent line. So that happens at 0. So that's how I come up with that. You want to be real clear on the difference between those 2 things. So what happens on this is we're going to be continuous everywhere except where we're discontinuous. So from here to here, That's negative infinity to negative 2, you're continuous. Then from here all the way to there, you're continuous. There isn't any breaks in the graph from negative 2 to 2. Don't worry about the sharp point, the horizontal, vertical tangent line doesn't matter. Okay? And then the last thing would be from here 2 to infinity, you're also continuous. Okay? So you want to kind of look at, make sure you understand little exercises like that. Next thing I'm going to look at is differentiability implies continuity. So this is a theorem. It says you have a function. If it's true that f is differentiable, then f is continuous at a. So my question is, can you draw a function that's differentiable on an interval that is discontinuous at some point? Well, you can kind of think through this a little bit. Let's just say here's a, here's b. We need to draw something that's differentiable everywhere on that point. There's several things you can't do. So if you're differentiable, you would want to make sure that there's no breaks in the graph, no sharp points, and that there's no horizontal or vertical tangent line. So there's no way to do that. So, okay, so basically if you're differentiable, then you're forced to be continuous. Okay, you got an interval where you're differentiable, yeah, you're guaranteed to be continuous. Now let's look at this backwards. So now the next question is, does continuity imply differentiability? Well, if we look at a graph on this, what I'm trying to do with this is, let's draw something that's continuous on A to B. That's continuous, right? Is it differentiable? No, it's not differentiable there. So it does not imply differentiability. Okay, that's one way to look at that. Here's another example. Here's A, here's B. I'm going to draw a graph that I think is continuous. Okay, that's continuous. There's no breaks in the graph, but it's not differentiable here because you have that vertical tangent line. So it's no. Okay, it works one way, but it doesn't work the other way. Okay, so the last thing I want to do is just a piecewise function. I just think this is an interesting graph to show students in a calculus class. So I'm going to have you put this in your graphing calculator. And we're just going to graph out this right here. So if I put this in, I'll have x sine of 1 over x. And let's do this let's do a window like negative 1 to 1. Or actually, let's start with like negative 5 to 5. No, I changed my mind. Let's go negative 1 to 1, just to start with. Okay, then maybe scale that by 0.1. And then for the y's, let's also go negative 1 to 1 and do the same thing, scale that by 0.1. Okay, so that's my viewing window. And here's the way you put this in. It's an interesting graph to look at. So if you also want to make sure you're in radian mode. Okay, so you need to move your graph to radian mode if you're not in there, and now we'll graph it. Well, it's kind of weird. It looks like it's kind of doing this and kind of doing some crazy stuff in there. So I want to show you this. This is just sort of a cool thing to show students on the calculator. We could continue to zoom in on this. So we could go like, one way to do this is zoom in. Press enter again, zoom in. Okay, and we could keep doing that. Oops, keep going. Well, it just looks like it keeps when you zoom in. It still looks like that thing is radically jumping around. Another thing you can kind of do on this is you can do what's called zoom box. So if you do zoom box, you draw a box around the area that you're interested in. So watch how I do this. Once I press enter, that gives me like a vertex of a rectangle. I go around like this. I always think this is so satisfying when I do this, okay? Let's zoom in. It still looks the same. It's still radically jumping around. So what you're going to find on that, even though it looks like, remember what happens on this is saying when x is 0, then you're at 0. Well, it looks like the limit is approaching 0 from the left and right hand side, but what will happen on this is it'll never hit 0. So this thing is actually discontinuous at x equals 0. You kind of have like a bubble, And then right next to it, it never connects all the way. It never does. The limit may approach 0 from both sides, but the function value never hits 0 until x is 0. All right, and for that reason, you would also be differentiable. You would actually be differentiable everywhere except 0. That's one that you got to think about a little bit. I mean, you just keep zooming in on that, and those values will never, the graph actually never connects like that. And you don't have a bubble. It's just kind of you have x equals 0. When x is 0, you have 0. But those y values just jump around. Even though they're tiny values, they never hit 0. It's disconnected. So that's a good problem for math majors that are in what are called real analysis classes. So I just think that's an interesting example to show students. Okay, so that'll wrap us up. Hope this helps everybody out on the topics of this.